Today I'll be talking about centripetal acceleration and tangential acceleration. Centripetal acceleration occurs when an object is moving in a circle, regardless of the change in speed of going around that circle. While tangential acceleration occurs when you're trying to speed up the speed of the object moving this circle. In other words, you're speeding it up or slowing it down. Alright, so let's talk about uniform circular motion. And in this case, we're not changing the speed of the object. We're only changing the direction. So the object moves at a constant speed in a circle. Therefore, there's only centripetal acceleration. And this is the acceleration directed towards the center of the circle, as we discussed in earlier videos. So, is there an equivalent angular units for centripetal acceleration? Well, we know that centripetal acceleration is velocity tangential, or the velocity going off on a tangent, divided by r, as we derived in an earlier video. So, can we change this to angular notation? Well, we know that velocity tangential is r omega. So, we can replace velocity tangential squared with r omega squared. And as you can see, when the r's cancel out, we're just left with r omega squared. So we have the centripetal acceleration in angular notation of radians per second squared. Okay, now let's assume there's a changing circular motion. In other words, the object's speed is increasing. Therefore, there is an acceleration tangential since the object's angular speed is increasing. So not only do we have the centripetal acceleration acting towards the center, but we have a tangential acceleration acting off on a tangent, because the plane is speeding up, going faster and faster and faster around the circle. And obviously you still have the centripetal acceleration because, well, it's still moving in a circle. The total acceleration is the vector sum of these two. All right, let's try a problem. Starting from rest, the thrower accelerates a disk to a final angular speed of 15 radians per second in a time of 0.270 seconds before releasing it. During the acceleration, the disk moves in a circular arc of radius 0.810 meters. And what we'd like to do is find the magnitude of the total acceleration. So not only do we have to find the tangential acceleration, but the centripetal acceleration, and add the two together as vectors. And since we're only looking for the magnitude of the acceleration, we don't have to worry about the angle. But we could easily find the angle if we wanted to. Okay, so here we go. Let's find the centripetal acceleration first. Centripetal acceleration is rho omega squared, as we just derived. Plugging the two numbers, we come up with 182 meters per second squared. And to find the acceleration tangential, we know that's r times alpha, and alpha is the angular acceleration. So another way of writing angular acceleration would be the change in angular velocity over time, and that's what we did here. We come up with 45.0 meters per second squared. And now to find the total acceleration, we would add the two together as vectors, which you are all well aware of how to do at this point. Okay, the last topic I would like to talk to you about today is what's called the right-hand rule. Grasp the axis of rotation with your right hand so that your fingers circle the axis in the same direction as the rotation. Your thumb points along the axis in the direction of angular velocity. So here you can see the fingers are wrapping around counterclockwise and your thumb is pointing up. So the direction of the angular velocity is upwards, while here it's downwards. And obviously it's really important that you use your right hand. I remember in college watching kids take a test on this subject, and they were writing with the right hand and using the left hand to do this, and all their answers were completely opposite of what they should be, which was kind of ironic. But anyhow, that's it.